Day 56 notes the topic is logistic equations. So the giraffe on steroids over here is a representation of carrying capacity. The giraffe can only put on so much weight before its skeletal structure can't support that weight. And environmental systems are like that as well. The upper limit of some sort of a system is called the carrying capacity. So when we have growth of something, there's often an upper limit called the carrying capacity where that growth slows and even stops. So what you're looking at here is a curve that is a solution to this differential equation. The change in the amount over time equals a proportionality constant and then the product of these two parts here. And what happens is when y is small compared to L, the fraction y over L, if y is small, becomes close to 0, and you've got dy dt, or the growth rate, is k times y. We solved this earlier. That's exponential growth, and that's this portion of the curve. But as the number of items approaches L, then this fraction here, as y approaches L, you would get L over L, which becomes 1. And so 1 minus 1 is 0, and the growth rate dy dt equals 0 for no growth, which is what happens when you get up here. At halfway through this curve, you change from concave up to concave down. So before that, the growth rate is increasing. After that, there is still growth, but its rate is decreasing. So the second derivative here is positive, increasing growth. The second derivative here is negative, decreasing growth rate. Our primary job today is to be able to solve this differential equation. We're going to take this and turn it into the logistic function. It's going to seem a bit like this kind of a lecture, but if you practice it a couple times, you should be able to do it on your own. You will be expected to solve this on your own. So here's the process. Separation of variables means that I need to move the dt to the right side, and since I have dy, anything with a y needs to come to the left side. So both this y and this entire parentheses needs to come to the left side and move into the denominator. Now we need to go through a bit of a detour. Everything in the green ink is a detour through partial fractions. This denominator needs to be split into two parts. In other words, we want to take this fraction, 1 over y times parentheses 1 minus y over L, and separate it into two separate fractions with the two distinct denominators. So partial fractions, I don't know what the numerator is. I don't know what the numerator is. I'm going to solve to figure out what those constants a and b are. Cross multiplying brings the left side as 1 on the right side. When I bring this denominator up here, the y's cancel and I have a times the remaining parentheses. When I bring this and apply it to the second fraction, the parentheses cancel and all that's left is a y times b. Okay, we need to solve this for a and b, and there's a couple different methods for doing partial fractions, but I like to look at constants versus variables. Distributing the a and writing it out this way tells me that there are two terms that are constants, 1 and a, and there are two terms that have variables, y, this term and this term. Since these are the only two terms that have constants, I know that a must be 1. When I substitute 1 in for a, this one and this one cancels out. This a becomes a 1. The negative y over L moved to the left side, produces this statement here, y over L equals by. Since the y, we're looking at the variable terms, I know that b must equal 1 over L. And so we've finished the partial fractions problem. We know that a is 1 and b is 1 over L. If I take the second fraction with its complex fractions and multiply the top and bottom by L, the second fraction becomes 1 over L minus y. That's the end of our detour. If I want the antiderivative of, in order to solve this differential equation, I want the antiderivative of this statement here. I'm going to separate it into the antiderivative of the first, and the second results from the partial fractions, and that's going to be equal to the antiderivative of the right side over there. So natural log here, natural log there, kt plus c here. One step that people tend to forget is that because this y is negative, we need to factor that in and make this separator here between the two natural log statements a negative. Okay. Now, for reasons that'll become clear in a second, we're going to switch sides for both of these things. So kt plus c is going to move to the left side and become negative. These are going to switch to the right side and exchange places. So now I have the natural log of L minus y minus the natural log of y. Combining using our log properties, L minus y over y, exponentiating both sides, we get this statement here. Now we need to solve for y. We're trying to come up with a logistic equation, y equals. So I bring this y up. Okay, when I bring this y over, I would have y times these parentheses plus y. Well, I can just factor out a y from both of those terms and get y times this statement. And now we're done. Divide both sides by the big parentheses, and the logistic equation for the number of items in a logistic growth situation is carrying capacity divided by b and k are constants, so b times e to the negative kt plus 1. And again, you should be able to go through this process from memory. So start with this differential equation and practice solving it. Okay. Oh, one thing I failed to mention, you're going to change this e to the negative c into just a different labeled constant. Okay, e to the negative c is just the constant, so we're calling it b from now on. Okay, last slide. Now we're going to apply our logistic growth equation to an example. So, number of people infected by a virus often grows like a logistic curve. Suppose that 10 people originally have the virus, and after 2 weeks, 330 people are infected. Assume that in the long run, about 5,000 people will be infected. So the three pieces of information you're given are the orange, which is like an initial condition. At time 0, 10 people were infected. The purple, which is another point along this growth curve. So at 2 weeks, 330 people are infected. And in the long run, 5,000 people infected. That's a carrying capacity. Now you might say, how do they know what the carrying capacity is? There are biological ways of estimating that, and there's also some numerical ways of producing an estimate for this. We don't go into how to produce this estimate, but you'll be given often that L value. So practice on your own, starting with the differential equation and turning it into this here. And now our first job is to use these two ordered pairs to find the two constants, b and k. First ordered pair is 0, 10. If I plug 0 in for t and 10 in for y, we get this statement here. Cross multiplying, I'm going to bring the 10 over here and get 500. b times 1 plus 1 is on the left side. Subtract 1, you get b is 499. Okay. Now we're here. We have one more constant to find, the k. So I'm going to use the second ordered pair, 2 and 330. 330 goes in for y, 2 goes in for t. And this time I'm going to solve not for k, but for e to the k. We've got to be a little bit careful because there's a negative sign here. So again, cross multiplying, I've got 500 over 330. This comes up to the left side, so I'm going to move the 1 over and get 5,000 over 330 minus 1. Divide by 499. And then since I want e to the k, I'm going to raise both sides to the negative 1/2 to get rid of that negative 2. So since it's e to the k to the negative 2, raising each side to the negative 1/2 cancels that out. We've got e to the k is this. Since I need that number and since I need it to be precise, I stored that in memory A. Do not round this number. You're going to use it later to make predictions, and you don't want this to be rounded. So our logistic equation is this. And now we can start answering questions. Estimate the length time until the rate at which people are becoming infected starts to decrease. The rate starts to decrease at the halfway point of your growth. So if you're told the carrying capacity is 5,000, then the halfway point is 2,500 infected people. Okay, so I'm going to plug 2,500 in for y, and now I'm going to solve for t. Okay, so take 5,000 divided by 2,500, you get 2. Move the 1 over, you get 1. Divide by 499, you get 499. So we have e to the k, which is 5.93 ... raised to the negative t is 1 over 499. The first step is getting rid of that negative sign. So if I reciprocate both sides, what was a negative exponent becomes a positive exponent, and the reciprocal of 1 over 499 is 499. Logging both sides allows me to move the exponent out front. Solving for t, we get this, and it appears that at about 3.488 weeks, we will reach the halfway point. The growth stops accelerating and starts decelerating. We switch from concave up, concave down. So the answer to B is about 3.5 weeks. And then when is the rate of infection growing the fastest? At that same point. At about 3.5 weeks is the fastest growth rate. After that, it starts to slow down. So that's it for day 56.